Today we have to learn to draw the MO diagram. Before that, what we discuss orbitals from metal ion, and secondly we discuss the shapes or orientations for orbitals from ligands. How many ligands are there? 6 ligands, and these 6 ligands will form a group, and that group orbitals will be ligand symmetry orbitals or ligand group orbitals. About metal ion, in general sense, if I have to say 3D orbitals, 4s orbitals and 4p orbitals are available. If I clearly represent them, then 3D orbitals means Eg plus. Help me. Eg plus.
A1G.
No. D orbitals. 5 d
T2G.
orbitals are there. Yes. Doublet means E. Doublet 2 orbitals consider. Left now 3 out of 5. Yes. Now 4s orbital means
A1G.
A1G.
good. And 4p orbitals means
T1U.
T1.
good. T1u. Out of these 9 orbitals, one set or one kind of orbitals, one symmetry orbitals are not suitable for sigma bonding. Which is that?
4P.
No. 4p is axial orbital. 4p means along axis, and ligands also come axis. Orbitals which are not along axis. Right. These
T2G.
T2G orbitals are there which are not suitable. So only these EG, A1G and T1U about which we have to discuss. Now let us talk about their energies. I have these 3 orbitals now. T2G are there, but along d orbitals are there, so along with EG they will be there, no? Their existence will be there. But bonding, anti-bonding orbitals, they can't form in case of sigma interaction, but orbitals are there. I'm asking question to you. I'm with now these 3D orbitals, 4s orbitals and 4p orbitals. How can I arrange them in increasing order of energy? Yes, whose energy will be highest?
4P.
Yes, 4p orbital energy is highest. So I represent the 4p orbital here. Okay, set. Yes, below that who will be there?
4S.
4S.
Are you sure? Yes or no?
Yes, sir.
Okay,
Yes.
it's right. 4s. Below that who will be there?
3D.
Right, 3D. While filling the electrons or for Boole principle, maybe in your school days, college days, or even F.Y.B.Sc you studied Boole principle, 4s orbital has low energy than 3D. It is a general concept which is applicable for elements up to calcium. May not be necessarily applicable for others where complications are there in the energy levels. 4s and 3d orbitals energies are comparable. So few electrons enters in 3d, then the 4s. Likewise, situation remains in the atom. But in case of ions, at least positive oxidation state remains, and there remains which are the 2 electron in the 4s orbital, they go out. So 4s there remains no electron. Electron 3d do remain. So we say 3d orbital is of low energy, then the 4s and then the 4p. It is very perfect. This is an energy sequence and it is important for us because to establish or form the molecular orbitals, combining orbitals should be of, yes, 3 conditions I told you before. Which were those 3 conditions? First condition, combining orbital should be of
Similar energies.
good, similar energies, brilliant. Second condition was
Same symmetry.
same symmetry, and third condition was
Appreciable overlapping.
there should be appreciable overlap. Brilliant, brilliant. So I'm asking you to bring attention to first condition, similar energy, and therefore we are arranging them in terms of increasing or decreasing order of their energy. Second condition, there should be the same symmetry, and that same symmetry aspect is covered here. If we are considering EG set from the metal, then from ligand also we will consider EG set. If we consider A1G set from the metal, from ligand also we will consider A1G set. If I consider T1U set from the metal, then from ligand also I'll consider T1U set. So there is no ambiguity about the symmetry. Symmetry is well considered here. Considering the approach of the ligands along the axis, we are representing their orientation, and those points are already covered. So about symmetry, we had a discussion. About appreciable overlap, There's no need of discussion because without that molecular orbital is not going to establish. And if molecular orbitals are establishing, compound is going to form, then certainly there will be the appreciable overlap. But for the sake of understanding purpose, that point is given. We will focus here on the energy and the symmetry. Symmetry aspect is covered in last two lectures. Now we are talking about the energy, and today we'll discuss actual formation of the molecular orbitals. You should know the energy sequence for the metal ion orbitals. Therefore, just I discuss this point. So is this point number one, that's the orbitals from metal ion and energies, is it clear?
Yes, sir.
Yes, sir.
Yes.
Okay, okay, good. Go on replying. No, be spontaneous to reply. If not clear, then you can ask me. Yes, anybody any problem for this point number one? Because from boys I found no reply.
Yes, sir.
Clear, sir.
Ah, okay, okay. I hope it is clear. Therefore, yes, is there. Okay. Now ligands are six. So six individually we are not considering. We are considering there's a team. We are considering there's a group, and that group will be with the orbitals. And about that I told to you. Those orbitals we say as a ligand symmetry orbitals or ligand group orbitals, and those orbitals which have this symmetry, e.g., A1G, T1U, those will mingle, those will what interact and will form respective orbitals. If there's a constructive interference, constructive interaction, then the bonding orbital. If destructive or negative or opposite, then there will be the anti-bonding orbital formation. Now, for ligand, orbitals directly we are accepting as a symmetry point of view. Means those are there. Actually, 9 orbitals are there on the met line. Out of those 9, only 6 orbitals are suitable because we are considering sigma bonding, sigma molecular orbitals. So axial orbitals we will consider. So orbitals which are not along axis are not considered for interaction. So will anybody inform me which orbitals we are not considered from met line, which set we are not considered from met line? That will remain non-bonding. That will not involve in bonding antibonding. That will not involve for constructive destructive interference because friends are not there. Orbitals from ligand to combine are not there because we are considering sigma bonding. Yes, which orbital we have not considered here? It was represented, then I removed that, I erased that orbital. What was that orbital? Which will remain non-bonding now?
T2G.
Right, that is a T2G orbital or T2G set. That will remain non-bonding and other orbitals will be used for interaction. Is this point number 2 clear? Point number 1 about metal ion orbitals. Point number 2 about ligand symmetry orbitals. Orbitals present on ligand group orbitals, their symmetry same because of point number 2 we are considering same symmetry. Point number 2 means this one, essential condition of molecular orbital formation. We are considering the orbitals of the same symmetry. So up to here, if clear, shall I move next now?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Now we have to discuss about the formation of the molecular orbitals. So I need to arrange them in particular energy sequence. While formation of molecular orbitals, we divide those things into 3 parts. The first part we consider orbitals. Orbitals from metal ion. It's the one part. Second part, we will consider the establishment of molecular orbitals for complex. Yes, will anybody answer? What is the name of the complex? Octahedral complex we are considering. General formula of
ML6.
the right, ML6. Octahedral means 6 ligands we need to consider. So it will be our second compartment. And third compartment, yes, help me. Which orbitals of ligand? Of 6 ligands. Yes, which orbitals we consider for ligands? I told you before. Which orbitals from ligands? That ligand forms what?
Group orbitals.
Right, right. Ligand from group. Ligand forms team. So their label is 3 letters are there. Which are those? L for ligand. Then just label came. Just somebody
GO.
answered. LGOs. LGOs. See apostrophe. Or LSOs, ligand group orbitals or ligand symmetry orbitals. Let me write one by one. Orbitals from metal ion. I represent d orbitals. 1, 2, 3, 4, 5. Students could able to read that those orbitals, 5 orbitals.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Those 5 d orbitals I considered. From ligands, 6 orbitals are there. I label them. Which orbitals I am considering here now? Which orbitals are there? Yes.
3D.
3D. So those will divide in 2 parts, T2G plus EG. Okay, it is a one part. Now I want to consider second set of orbitals, or only one orbital is there. That is the 4s. 4s. What's the label for 4s orbital?
A1G.
Good, A1G. Now I want to consider third set of orbitals. What is the third set of orbitals? Yes, somebody help me.
4P.
Yes, 4p. What's the label for that?
T1U.
Yes, T1U. Now orbitals are from ligands, and those ligand orbitals, actually group orbitals, and number we consider as a number of ligands. I want to ask you the question. Let how many orbitals from the ligand be? What will be their energy? Energy for ligand orbitals will be lower than that of the metal orbitals or will be higher than that of the metal orbitals?
Higher.
Why? On what? Which factor energy depends? Energy depends on electronegativity. Carbon, oxygen, CO molecule you have studied, NO molecule you have studied, HCl molecule you have studied, even this year BH2 molecule you have studied, H2O molecule you have studied. There see, two different atoms were there. Those were combining. If we consider H2O, orbitals of oxygen and orbitals of hydrogen. In case of CO, orbitals of carbon and orbitals of oxygen. What is the conclusion? I inform you the rule. More electronegative species is energy will be lower because nucleus will attract the outer electron. No shrinking will be there. Energy will be what? Lower. So oxygen energy level is lower than that of carbon. Respect to orbitals. 2s orbital of carbon, 2s orbital of oxygen. 2p orbital of carbon, 2p orbital of the oxygen. So more electronegative species energy remains low. Now answer for my question. So it will help you to conclude. Metal ion and ligands. Two things are there. Among these two, who is electronegative? More electronegative.
Ligand.
Right. So whose energy should be low?
Ligand.
Yes. So ligand orbitals, see 1, 2, 3, 4. How many are there?
6.
How
5,
many ligands are there?
6.
Ligands, how many are there? 6 ligands are there. Here, you see what answer? Same mistake students do commit there in examination. They write there the 5 ligands. Yeah. 6 ligands are there. And what are the symmetry orbitals there? Yes. First is Eg, 2 plus. I told you whichever the suitable orbitals from metal ions are there, that will be the symmetry for the orbitals of the ligand. Eg that I consider plus.
A1G.
Yes, only one. T2G will not be there. Remaining will be there. Plus.
T1U.
TIU.
Right. T1U. These 6 symmetry orbitals are there. Ligand symmetry orbitals are there. LSOs are there. Total 6. In that one thing is not there. That is what the T2G. And I represent the orbital which is not there as a non-bonding orbital. See here. T2G. T2G means how many orbitals will be there? How many dash I should represent there? 1. How many?
3.
2. Yes. And 3 dots are there. That's our T2G orbital. Energy of T2G is not changed. Which is the previous energy is there. Same energy is kept there. Same energy. Energy is not changed. Now molecular orbitals when we establish, just a bit, so that little space I may need here. Okay. Now you have to imagine actually 3D orbitals from metal ion, then 4s orbital, then 4p orbitals. Energies are suitable. What I'm talking? Energy for this ligand and energy for metal ion. It's an energy arrow. Energy is increasing. Energy from orbitals of the ligand and orbitals from the metal ion. Those are suitable. Means this 4p orbital also is suitable to combine with the orbitals from the ligand. Though the energy seems to be the larger, but they are suitable. They can overlap. Up to what extent they will overlap, that we need to discuss. So in metal ion, what happens? 3D levels are there, 4s levels are there, and 4p levels are there. It is a sequence of energy in a metal ion, and metal ion is the center. And from surrounding along the axis, 6 ligands are coming, and those orbitals are mingling. Those orbitals are interacting. It is true, where easily one can understand that Eg orbital will combine with Eg, A1G orbital will combine with A1G, T1U orbital will combine with T1U, and wherever I said combination means interaction, means overlap, then there are two possibilities, one of addition and other of subtraction, one of constructive interference and other destructive interference, one of decrease in energy and other of increase in energy, one of bonding orbital and other of anti-bonding orbital. Students could able to understand what I'm saying.
Yes, sir. Yes. Yes, sir.
Okay, so if I consider Eg from the metal ion, then Eg from ligand, they will combine to produce one bonding, one anti-bonding. Eg bonding and Eg anti-bonding. If I consider A1G from the metal ion, A1G from the metal ion, and A1G from the ligand, so they will combine to produce A1G bonding and A1G anti-bonding. If I consider T1U from the ligand, then T1U from the metline, they will combine to produce T1U bonding and T1U anti-bonding. Bonding means low energy. Anti-bonding means high energy. Low energy compared to barycenter, medium, average energy. Or you can say lower energy orbital. How much energy value decreases, so that much amount of energy will increase from the other higher energy orbital. Now only just listen. So those group orbitals or suitable symmetry orbitals will what combine to produce molecular orbitals. Now all three possibilities are there. T1U can combine, A1G can combine, EG also can combine. Now I have to think which orbital will combine strongly or which orbital will be of low energy. See, if I have to interact these ligand orbitals with 3D, 4s and 4p, EG, A1G and T1U, and ligand groups are coming. Ligand orbitals are coming. They're interacting. What do you think? Who will be with strong interaction? More overlap. Interaction means I'm saying more overlap. I repeat, listen carefully. I am with EG, T2G timing I'm not considering. I am with A1G and I am with T1U. EG, A1G, T1U. It's an energy sequence or orbital sequence in a metline, and metline is the center. Now ligand group orbitals, ligand symmetry orbitals are combined. So with whom there will be the strong overlap, with whom there will be the strong interaction. Three options are there with you.
EG.
EG, A1G, T1U. Yes, yes, please. No, somebody answer. I could not hear that answer. Is my question clear?
Yes, sir.
Yes, sir.
Okay, yeah, okay. The answer no. Out of those three, you have to choose one option. Where there is a strong overlap, strong interaction. EG. Why?
Closer, both are.
Okay, okay. From energy point of view, EG orbital is closer. Energy point of view. But from position point of view, position. Ligands are coming from outside, no? Ligand orbitals are coming or approaching from outside, and metline orbitals are inside. When overlap takes place, orbitals do overlap, no? Electron cloud do overlap. When overlap takes place, overlap occurs. At that time, which orbital will experience first overlap?
A1G.
Why? See, logically you're not understanding. There is one chocolate. It is with three flavors: EG flavor, A1G flavor, and T1U flavor. Plus additional, but main flavors, these three are there. And chocolate is prepared in such a way, nucleus is at center. EG flavor, 3D. Afterwards, the coating is there, and the flavor of A1G. Afterwards, coating is there, and that's the flavor of T1U. And from surrounding you are coming. Means you are chewing that chocolate. Then which flavor you will come across first? Which flavor you will meet first?
T1U.
T1U.
Right. T1U flavor. T1 is a coating, no? Means actually you have to imagine the orbitals in the metline, and you have to imagine group of the orbitals, crowd of the orbitals, team of the orbitals is going to interact with the metline orbitals. Energetically, it is not so convenient. So convenient. See, so word is important, but it is convenient. So T1U orbital will experience strong interaction. Then secondary, which will experience strong interaction. It means compared to less interaction. Yes.
A1G.
A1G.
A1G. Afterwards,
EG.
EG.
EG. Okay, good. Now, what I do there, A1G representation I do here, because the energies of 3D and 4 is comparable. No? They're nearby. What happened diagram? A1G was little above. So I'm just doing that one change. See whether you understand it or not. Okay. This change, what I did here, previously A1G was upside. Now I brought that A1G little down. See, here I am considering A1G. Could you able to understand what I am saying? Yes or no? Still difficulty? See what I am doing. A1G was there upside previously. Here A1G was there. Now I am bringing that A1G little down. Down means here I represent that A1G. Why? For this A1G and 3D, the energy should be less. No, energy gap should be less. Energies are comparable. Therefore, just I brought it down for our next suitable explanation. Is that change clear?
Yes, sir.
Yes, sir.
Okay, little change I am doing that. Okay, now see, as per your logic, 4p strong interaction, then 4s, then 3d. So which orbital should be there here down? Lowest energy orbital, molecular orbital, because of T1U, because of A1G, or because of EG? Bonding orbital means low energy. Anti-bonding orbital is high energy. High strong the bond, more strong the bond, lower will be the energy for bonding, and accordingly higher will be the energy. Yes. Which orbital should I represent here down now? At down, T1U, A1G, EG, these are the three orbitals overlapping here. And you told me that T1U will experience a strong interaction, strong overlap, because from outside, first time T1U will approach. First facing T1U will do. With whom? ligand group orbitals. It's not so suitable, but suitable. Afterwards, they come across other friend, A1G, more suitable. Afterwards, they come across friend EG, further more suitable. So, suitability point of view, EG is best. But from approach point of view, T1U is top. And afterwards, overlap is important. No? Suitability is there, but overlap with whom will occur? Third essential condition to form molecular orbital. There should be appreciable overlap. When there will be appreciable overlap, if orbital is extensively interacting, and with 4p there is appreciable overlap. So point number 3 is more suitable for 4p. So there is a competition. From overlap point of view, 4p is best. From energy point of view, EG is best. But energy is not a practical approach. Reality is there. Unless and until overlap takes place, energy can't do anything. Two hydrogen atoms are there. They could be able to overlap. But if I keep one side, the other side, no approach, no interaction, no overlap, no molecular orbital. So overlap is a dominating point here. And because of that, 4p orbital, energy should be low. But energy will low from here. See here. Energy should be at the considerably low. It is expected. But when 4p and 4s comparison takes place, suitability of energy and position, it is found. Now just listen. After some doubts come, I'll discuss. It is found that a A1G orbital remains of low energy, lowest energy. It is a A1G. It is a bonding orbital. And anti-bonding A1G orbital is not that much of lowest energy. See here. The energy with which it decreases. Just wait. I remove that now. Energy with which this A1G decreases, with that much amount of energy, A1G will increase for the anti-bonding. Now see, decrease I am showing here. See, from ligand orbitals, I am bringing A1G down. See, here is a A1G orbital. This is a decrease in energy. 1, 2, 3, 4, 5, 6, 7 dots. Time being considered. A1G from here will increase. 1, 2, 3, 4, 5, 6, 7 dots. Could you able to understand what I am drawing?
Yes, sir.
Yes. So upper orbital, high energy orbital is A1G star asterisk, high energy orbital, anti-bonding orbital, and low energy orbital simply A1G. Afterwards, what happened? Though T1U was there in the race first, and that race was won by the A1G now, lower energy orbital. Then turn come of the T1U. So T1U decreases 1, 2, 3, 4, 5 dots, time being considered. By 5 dots, I am decreasing the T1U. T1U set means I should represent by means of the 3 lines. Okay, I represent it now by 3 lines. 1, 2, and 3. As the energy decreases, similarly, T1U from here will increase. 2, 3, 4, 5. And here T1U. 1, 2, and 3. That is our T1U set. Upside, and this is a T1U set downside. So it is labeled as T1U. It's a bonding orbital, and it is labeled as T1U asterisk. Means it is an anti-bonding orbital. Students, are you following what I am drawing?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. Now, last orbital left. That's EG, that I show by the other color. The EG orbital, I decrease by 1, 2, and 3 lines. It is our EG set. Similarly, from here, EG orbital will increase 1, 2, 3 lines. It's a EG set. Complete this now. ... So it is our EG bonding. What label shall I give for anti-bonding orbital?
Asterisk.
Yes, EG asterisk. EG asterisk. This is our MO diagram. One additional point you need to mention, that is this splitting parameter. This one, energy gap between, this is our T2G orbital, non-bonding orbital, and EG star orbital. Yes, what is energy gap? It is equal to delta. In crystal field 3 also it that energy gap is delta.
O.
Yes, delta O. Octahedral complexes we are studying. So delta. So what crystal field theory did, same thing is here. In crystal field 3, mistakenly T2G orbital was low energy. In molecular orbital 3, is not a mistake, it's a reality. And mistakenly T2G orbital came lower, EG orbital came higher. In case of octal complexes, crystal field theory was correct. Because what is the basis of crystal field theory? Repulsion. Don't just simply answer my question. I am with 2 sets. axial and non-axial, Eg and T2G. And ligands are along axis. And if I'm considering repulsion, then which orbital will increase? Eg orbital will increase energy. That's a crystal field theory. But if ligands are approaching along axis, there's a bonding between metal and ligand. No, I repeat, repulsion is the base for the crystal field theory. For that, it is right. But what is the reality? What are we finding there? What are we forming there? We are forming complex. We are forming coordination compound. That's a ML6. Whenever you form any compound, then there's a bonding. And wherever there's a bonding, there's attraction. Means resultant attraction is there. Repulsion is there. But result is attraction. Therefore, bond form. But what crystal field theory consider? Repulsion. Repulsion is not scientifically acceptable for the net attraction. And if net attraction is considered, suppose, then which orbital should experience more attraction? Eg orbital should experience more attraction. So energy of Eg will be low, which is not. So that's a theoretical failure of the crystal field theory, which can be described here by molecular orbital theory. Then all other magnetic properties, stability, those things which are explained by crystal field theory could be explained by molecular orbital theory. But especially for stability, still we take the help of the crystal field effect. So which are the limitations of VVT are there? No. All we can overcome by studying the crystal field theory or say molecular orbital theory. So this only one diagram is there in your syllabus and various molecules are there. And we to apply this MO diagram or this molecular orbital theory approach to all other molecules to produce or to explain their magnetic moment or stability. Stability is a measure of splitting parameter. So today I want to emphasize the formation of the molecular orbitals. Shortly I tell you, listen carefully now. I am summing up the lecture now. Metal ion is with the 9 orbitals. Out of that only is 2, 1 and 3, 6 orbitals are suitable visually, e.g. A1G and T1U. As per the basis of the molecular orbital theory, ligands also should be with the same orbitals, e.g. A1G and T1U. Yes, 6 orbitals from ligand, 6 orbitals from metal ion, they will overlap to produce sigma bonding. Then orbital which is not involved in that sigma bonding, that is a non-bonding, that's a T2G orbital, first layer represented. Then there is a competition in the overlap. The outer coating is of the 4p. Outer coating is of the T1U and the T1U orbital will overlap with the T1U orbital from the ligand. So since it is outer, it is expected there is a more overlap. Overlap point of view, T1U wins, but from energy point of view, EG wins. The A1G orbital from overlap point of view, less, medium. Energy point of view also medium, but its energy is nearly equal, near to 3D. So energy point of view is a more conquerable. So ultimately, the competition is won for bonding orbital by A1G and it is of the lowest energy. For sake of example, I told you 7 dot decrease and accordingly 7 dot increase. 7 dot decrease from the low energy A1G, that's the ligand, and 7 dot increase from high energy, that's a metal ion. Then comes the 4p, that's a T1U, decrease by 5 dots from ligand and decrease by 5 dots, increase by 5 dots from metal ion to produce antibonding orbital. Similarly, now last, that's a EG, decrease by 3 dots from ligand, increase by 3 dots from metal ion, and the energy gap between EG star and T2G I represent as a delta O. It's a basic concept of molecular orbital formation for octahedral complexes. And to come to this diagram, we started with the metal ion orbitals, suitability of metal ion orbitals, means suitable metal ion orbitals for sigma bonding. Then we come to the ligand orbitals, suitability of ligand orbitals. Then we come to their energy levels, their symmetry, their extent of overlap, and we established the MO diagram. Important point is this one, energy level. Energy level increases from bottom to top. Yes. Is this explanation, is today's teaching clear to you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, friends, then you have to prepare the notes. Now I'm uploading the videos. At this moment, I'm working for FY, then I'll work for SY. All pending videos are there. And then I'll come to your class. All pending videos are there. I will upload up to tomorrow. Only and only that work is there with me. I will do that. But your work is to complete the assignments. And you do that. Last semester, I appreciated your work. Really brilliant, dedicated work you did. Everyone did. It is a proud moment for me. Similarly, I want students this semester also you do work. Yes, are you ready to work or not?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Start your work. Only I have to assign. I have to give the assignment. And when feedback was asked, you said no, that assignment completion helps for the preparation. Yes, do well. You are here to study and we are here to teach you. And when studying a problem comes, again the discussion we can do. So today follow-up session I could not do, Miss crystal field theory discussion. Next time we will do that follow-up session because I wanted to cover this MO diagram. And once this MO diagram is clear, no, then any molecule come in the examination, and certainly it comes. You could able to answer the question. A1G, T1U, EG, T2G in between, EG star, A1G star, T1U star. That's the sequence. So at the bottom, 4s orbital, A1G comes. But at the top, T1U is there. Likewise, you mingle, you play with that diagram, you work with the diagram, spend time with the diagram. Neuron will do automatic work. Don't worry for that. Worrying for neuron, worrying for memory, you lose the time, you leave the time, you waste the time. Okay, so go on playing with these terms, symbols, energy levels, and these complexes. You will make the molecular orbital theory yours. Understanding will be yours. Okay, is there any doubt? Any question? Anything anybody wants to suggest? Okay, I'm finding the replies here. Okay, students, now I stop the recording and I declare here today's session is over.